What?
When it goes
Is it
without
TS or what is
compression?
Yeah, so when it sends it, so if this starts, like imagine this is neutral. So when that goes towards me, that compresses the air. Okay? But then when it pulls back, then it creates like a vacuum. Then when it goes towards it, creates another compression. So when it vibrates, when it's going towards me, that's compression. Pulling back, that's a rarefaction. So here's kind of a cool equation if you've ever played any kind of string instrument. So TS is the tension. So what unit is tension measured in? Newtons. Okay? Now, this is mu, which is, this is not the coefficient of friction. This is called, it represents mass per unit of length. So since it's mass per unit of length, what units is mass going to be in? Kilograms per meter. Now, here's the cool part of this. What's another way to express newtons? Kilograms meters per second squared divided by kilograms per meter, right? So, since that's kilograms per meter, the kilograms are going to cancel out, but what's going to happen to the meters? That's going to flip up, and you're going to get the square root of meter squared over, otherwise known as velocity. Okay? Now, what this represents is the speed of sound on the string. So, here I've got a basic banjo, okay? And if you notice on these strings, all of these, okay? But some of them are thicker, right? Which are going to have a bigger mass per unit of length. And then you can adjust the tension. So, let me do this one. So as I change that tension, it vibrates at a different frequency. Okay? So by changing that tension, if you look at this mathematically, each one of these has their own mass per unit of length. I can't change that. Okay? That's a fixed value. Well, but I can change the tension. Okay? So if you look at this, and again, this is the velocity as it goes along the string. And any velocity is still frequency times wavelength. So if I increase the tension, so let's go with so if I increase the tension, assuming that the mass per unit of length stays the same, what's going to happen to the velocity? That's going to increase. But now, that is not the speed of sound. That is the velocity as it travels on here. But what you hear as difference is that as you alter the speed that that wave travels down the wave, down that string, that alters the frequency that the string vibrates at. So if I change the frequency that the string vibrates at, that changes what you hear. So when you tune any kind of string instrument, you're basically taking advantage of this equation. So each string, some of these are really, really small, which has a very, very small amount of mass per unit of length. Others are much bigger, those have a bigger mass per unit of length. So the tension is your equalizer. That's adjusting that tension, adjusts the speed of the sound. That's not the speed of sound. Listen to me. That velocity is not the speed of sound. It's the velocity on the string as it vibrates. But as that vibrates, so you basically have kind of two different things going on. So you have the string as it vibrates, okay? Just like I did with that spring, okay, when Gadfly was holding the other end of it, okay? As I changed that vibration, I changed the frequency because I was changing the speed. So as I change the speed, I change the rate at which that is vibrating. So you have this as the speed going down the string. But then that alters the frequency that it vibrates at. That frequency gets what gets plugged into the speed of sound, which is a fixed value, which is wavelength times frequency. So when I change the tension on the string, that changes the frequency that it vibrates at. As I change the frequency, that changes the wavelength of the sound. That changes what you hear in terms of intensity. So here's what I want you to get out of this. Assuming that velocity stays the same, which would be like the speed of sound, for example. That's wavelength times frequency. If you're old school, that's wavelength times nu. These are inverse relationships of each other, assuming that the velocity is constant. So if the wavelength gets shorter, the frequency gets, or if the wavelength gets bigger, the frequency gets smaller, because they're going to produce the same velocity. Okay? Now, energy. We've spent a lot of time talking about energy of sound. Okay? And there is a certain amount of energy to it. Okay? Somebody was really bored, and they estimated that if you could yell, "Ah!" like that for like 8 hours, and you could harvest that energy, you could make a pot of coffee. Okay? Now, what was the kids' movie where they Monsters Inc. Okay? Oh. Yeah, you knew exactly what I was going with that. That's crazy. Yeah, so in Monsters Inc., what did they harvest? The energy of screams. Okay? But then they figured out the energy of laughter had more energy. So if you look at energy being sound, okay? All right, okay? So when I talk, there's a certain amount of energy that goes out. So you all pick up just a small amount of that energy. Same thing is true of the sun. The sun produces a lot of energy, right? So our rock happens to absorb a small amount of that energy. What?
I forgot to turn the camera.
That's okay. You didn't miss much. We're just talking. Here's the short version of what you all just missed. The velocity of the string is tension over mass per unit of length. That determines how it vibrates. The speed of sound is a fixed value, assuming that the atmospheric conditions are the same, wavelength and frequency. Now, as far as energy goes, if you're talking specifically about light, okay, and this is specific to light, not sound, the energy in one photon of light, and this is just the opening salvo of this, we'll spend a lot more time talking about this. The energy of a photon of light is something called Planck's constant, which is the value of h. It's just a number. We'll get into the number later. And that's h times frequency. If you're old school, that's h nu. So here's what this means. And this is what I just showed you when I was vibrating that string. As the frequency goes up, that takes more energy. So what allows you to see different colors is because the photons of red light, so red light has a very long wavelength, violet light has a very short wavelength, okay? But they all travel at the same speed of light. So red light, with that longer wavelength, has a lower frequency, which is why, if you've ever seen a fire as it dies out, what color does it glow right before it goes out? Red. Okay, it glows red because that's the longest wavelength and the shortest, and the longest wavelength and the shortest frequency. Violet light has a very high wavelength, very short wavelength, so that has a very high frequency and a lot of energy. So this is why you don't see, as the fire dies out, it doesn't glow purple or green or anything like that, because it doesn't have the energy. It only has the energy to produce basically red photons. So this is how you can tell if you were a hardcore like physics nerd. Okay? So if you go old school and realize that's the Greek letter nu, okay? So E equals H nu. So if you solve this for nu, you get E over H. So if you're a hardcore physics nerd and someone says, hey, what's nu? And you go E over H, physics people will understand exactly what you're talking about. Okay? Most people would look at you like, what are you smoking, man? So that's how you, so that's like the inner sanctum joke. Okay? Olivia, today, ask your dad, hey, Dad, what's new? See if he remembers that. Okay? E over H. So that's how you can tell if you're hardcore. So anyway, all right. Now a little bit of voodoo that you can do, just a little bit. So we said mu is mass per unit of length, and this is an idea that we're going to use a lot. So I just want to kind of begin to lay this out. So if you go back to density, what's another way that you can express how can you find mass using density? Well, density is mass divided by. Oh no, that's buoyancy. Okay. So could I substitute density times volume over L? Could I do that? Legal. Okay. Now, if you have a string, if you think about it, is a cylinder. Okay? How do you find, if you have a cylinder of a certain length and a certain cross-sectional radius, how can you find the volume of a cylinder? Pi r squared times, or lengths in this case. I want to put it in terms of length. Okay? So your pi r squared is your cross-sectional area, L is the length. Do you get the correct units? Sure. Because radius squared is going to be in. Meter squared length is going to be in. So I get meters cubed, which is volume. Okay? All right? Cool. That. So I can write this as density times pi r squared L. But then I'm going to divide by L. So you can also express that as density times pi r squared, which could be also your value of mu. So you actually don't have to have the length. Okay. Got that, got that, got that. What?
Why is density a P?
It's a Greek letter rho. Yeah, it's technically the Greek letter rho. It's not P, it's a Greek letter rho.
What is
Okay.
that?
So here is probably the shortest assignment I will ever give you.
A cylinder?
Okay?
I'm confused with that.
So this is out of chapter 15.
Yeah, that's a cylinder. I'm just gonna
Please give us like 20 questions or something, please.
Can you give me one question?
All multiple choice. Yeah, it's pretty good.
Wait, no, what?
They're also all multiple numbers.
That's it.
I like that.
So
Now, it does talk about the speed of sound in different materials. And there's a chart that actually lists that. So here's the dichotomy of sound versus light. Sound in air is relatively slow. So sound, if you transmit it through like a solid medium, so if you increase the density of the medium with sound, it actually travels faster because the particles are closer together, and so it travels faster. So with sound, the denser the medium, so like water, sound in water travels much faster than sound does in air. Light is just the opposite. Light travels slower in water than it does in air. So with light, if you increase the density, you actually slow it down, okay, which is how refraction works, which we'll get into later.
Wait, so that's why, like, in the winter, you can, like, yell for it.
What?
No, that's, that's because
Where did you
you're
get
working
that?
against that energy going out. Okay, there you go.
Where's that from, right?
Yeah, stop y'all with camera, Mark.